Alright, hello class. Alright, so today we're going to go over something called the ideal gas law. So, what that is, let's say we have a container that is filled with gas. And the gas molecules could be atoms if you have something like helium or neon, but mostly you'd have molecules. You know, they're moving around pretty quickly. So, say we look at one molecule, it's going to hit this wall and bounce off. And then it's going to, hit more walls and just bounce around. We'll talk more about how fast these molecules are moving later on, but, typically several hundred meters per second. They tend to be moving, so they're going to be bouncing off the walls. And of course, when it hits the wall's going to hit it back. There's going to be these forces exchange. And this molecule is going to exert an outward force on the wall of its container. Now, if you say you have a balloon, it's filled with air, and these air molecules are bouncing off of the walls. Say you hold your hand up to the balloon, are you going to feel like all these molecules hitting your hand? Of course not. First off, the force that an individual molecule exerts would be extremely small, way too small for you to notice. And the number that hits in even a short interval of time, because there's so many molecules and they're all moving, the number of collisions that the number of molecules are hitting are going to be simply enormous in even a short time interval. And so what you'll feel is kind of like the average effect. So on the walls of this container, we define pressure as force over area. So there's a total force on this wall due to all of these collisions, and if we divide by the area, we get pressure to measure in newtons per meter squared. So that's one property of this gas, is pressure. Another property, what does the pressure of the gas depend on? Let's look at that. And I'm going to say that the pressure is proportional to the number of molecules. So if you have twice as many molecules in this gas, you'd have twice as many collisions. You should expect double the pressure. And that's true to a point. Turns out if you cram too many molecules in there, they're going to start interfering with each other. And what we're talking about here, the ideal gas law, that actually breaks down at some point if you get an extremely dense gas. But for reasonable values, this is a very good, this is accurate. Pressure is proportional to the number of molecules. Now what happens if what if we change the temperature of this gas? Well, we know that the hotter the gas, the more rapidly these molecules are moving around. And if they're moving faster, they're going to hit the walls harder. And they're also going to hit the walls more often. Because they're moving faster, they'll be bouncing around more quickly, more collisions. And so that's definitely going to affect the temperature. Now, the book tries to show, I kind of am mixed on whether or not I like the book's approach to this. Because they say, say there's N molecules in the gas. And let's imagine N over 3 are bouncing back and forth in this direction, and 1/3 are going in this direction, and the other third, it's like they're all moving perpendicular to the walls, which is of course not true. But that's a simplification you need to make. But you can try to relate the how the pressure would depend on the temperature of the gas, or by considering these kind of crude models. I kind of go back and forth on whether I do that. It's a little too much of a simplification for my taste, though, so I kind of skip that approach. And we can take this as an experimental fact that the pressure is proportional to the temperature of the gas. So if you double the temperature of the gas, you double the pressure. Now, doubling the temperature of a gas, going from, say, 20 degrees Celsius to 40 degrees Celsius, that is not doubling the temperature, because this temperature has to be in kelvins. So 20 Kelvin to 40 Kelvin, that would be doubling the temperature. Just remember, in this equation, T has to be the absolute temperature, which means kelvins. And that's the only units that we would use here. Now, what about the volume of this container? What if we have a bigger container? Well, it's going to take longer for these molecules to hit the wall. Like, say it's going to hit this wall, and it's going to bounce around and hit the wall again. Well, the bigger the container, the longer that's going to take. And so we can also say that the pressure is inversely proportional to the volume of the container. Now, these are all individual experiments that were done. I forget the names. I remember Boyle's law is one of them. He was a very prominent scientist at the time. I forget the names of the others, though. But like each of these was an important discovery by itself, and so we can take them as experimental facts. To try to do this, it's actually pretty complicated to try to do this based on molecular collisions with the walls. We can kind of do it with this massive oversimplification that they all move perpendicular to the walls, but yeah, I kind of stopped going with that approach. So let's just say that these are, let's combine all these. We'll take them just as experimental facts. So we have NT over V. This is still a proportionality relation. And to turn this into an equation, we introduce a constant. This constant is called Boltzmann's constant. I'm going to double check that number. I think that's right, but let's see, K. Yeah, that's right. Okay, so it's 1.38 times 10 to the minus 23rd joules per Kelvin. That's Boltzmann's constant. Boltzmann was one of the greatest scientists of all time. Definitely up there. I mean, well, not like there's like Newton and Einstein and Galileo, but, you know, kind of just beneath that level. He was doing his work in like the mid to late 1800s, and he did some really amazing work on what's called kinetic theory. So he was looking at gases like molecules or atoms, and coming up with these really sophisticated models of how, you know, like you could derive the ideal gas law just by looking at these molecules, where he took into account like the distribution of velocities and that they're all going in random directions. And he did a lot of very important work on you know, explaining things in terms of this fundamental idea that the world is based on atoms. Now, unfortunately, this was in the 1800s, and it's kind of remarkable that, I was kind of shocked when I learned this, that the atomic theory of matter was still being debated until 1905. So atoms, they were accepted by many scientists before that, but they were still kind of seen as this abstract idea with no real experimental proof that they exist. Or, well, there's no such thing as experimental proof, but experimental confirmation that they exist. And so some scientists refused to accept them. And yeah, in 1905, that's when the debate was ended. It was actually Einstein that kind of was the final argument there. He wrote a paper, or I think, a couple papers on something called Brownian motion. It was named after a biologist named, I think it was Robert Brown, or his last name was Brown. And he was looking at grains of pollen in a microscope. And he saw them kind of bouncing around. And he said, okay, the pollen is, it's a biological thing. There's stuff going inside that's causing it to bounce around. But then it was discovered under a microscope, even inanimate matter would do the same thing. If you have small enough things, they get knocked around. And Einstein explained that as it's being bombarded by molecules on all sides. Now, if markers being hit by molecules on all sides, you don't see it getting knocked around. And that's because the forces involved are extremely tiny and, roughly equal numbers from both sides. But maybe in one small moment in time, like say a little more coming from this direction hit than that direction. That'll lead to a net force in this direction, if there are more molecules hitting in that way. But again, it's a large object compared to, these forces we're dealing with. And so it's not going to have any effect at all. But when you shrink down to a molecular level, or, things you can look at under a microscope, those slight differences in like the collisions coming from different directions, that will cause things to jump around. And again, it might sound like, well, big deal, anyone could have said that. But to actually, what Einstein did in his paper is he went in a lot of detail, like doing statistical analysis and explaining like the size of the particle and what kind of, motion we should expect from it. It was a really, they say he could have won a Nobel Prize for that. He never did, but that was definitely a Nobel Prize worthy paper by itself. Okay. So, Boltzmann, he did a lot of really amazing work, but then it was mostly ignored because atoms weren't fully accepted. And reportedly, he killed himself because he got depressed because no one would listen to him. And then atoms were kind of confirmed shortly after. Once they became accepted, everyone, it became very fully accepted. So, I guess he should have waited there. Okay. But anyways, this is more commonly written in this form. Just multiply by the volume. Okay, so what we have here, this is pressure, that's volume, N is the number of particles, K is Boltzmann's constant, and T is the absolute temperature. It must be in Kelvin. Now, what if you don't know how many molecules there are? Like, say we have, rewrite the equation. Like, say we have a container with a given volume and you've got 40 grams of some gas. You don't know how many molecules. You can always calculate that. We could just stick with this as the ideal gas law and move on. But sometimes you know the number of moles instead. And again, if you know one, you know the other. They're related by Avogadro's number. But we can write an alternative form for the ideal gas law in terms of moles. So n, lowercase n is the number of moles. And then we have this R, which is called the universal gas constant. And it's 8.31 joules per mole Kelvin. So again, if you know the number of moles, use this version. If you know the number of molecules, use that version. Of course, you could do either because they're related by Avogadro's number. And from this, we can also see this relation that big N times K equals little n times R. All right, that's the ideal gas law. That is a very important law. And again, it's called the ideal gas law. And any gas that obeys it is called an ideal gas. And basically, all gases do obey it under normal conditions. If you get to like some extreme conditions, like maybe a very, very low temperature or an extremely dense gas, they can, you have to modify this a bit. But we're never going to deal with cases like that. So any circumstances we deal with, this relates to pressure, volume, the amount of the gas, and the temperature. So very important law. And I guess that'll be it for the ideal gas law.